due to a current carrying wire. And this looks a lot like what we had before, where before we had QV cross P, now we have IL cross P. As I said, you can think of this current times the length a lot like QV. In fact, we found it has the same units, and it's really measuring the same thing, but instead of having a charge in free space, now we have a charge on a wire. So be able to work a problem like this, doing the cross product, or one of those like we did before where we have a particle in free space with a certain velocity. We're going to look at a few applications of this today. Like for example, the torque on a current loop. Let's say that we have a loop of wire like this, and it's in a magnetic field, and it's allowed to rotate about a certain axis. I can think about the forces that are acting on this. What is the force that acts on these side, on this side right here, where my current is in this direction and my magnetic field is in that direction? Both the current and magnetic field are to the right. Right, so here my force on this section is going to be 0. What about up here? It's also 0, right? Because in this case, excuse me, in this case the angle is 180, and in this case the angle is 0. And in both of those cases, that sine theta term goes to 0. Now if we imagine this thing rotating around, like if we rotate it so that this loop of wire is coming out of the page at you, then you're going to have a current, say up here, that's in this direction, and a magnetic field in this direction. And so there will be forces acting on this loop of wire. But because it's rotating, those forces, the torques are actually going to cancel out. That's all it means, just the way it's rotating. All right. We'll see that in just a bit when we look at a coil of wire. But anyway, in this case, our magnetic field on side A is going to be 0. Because theta either equals 0 degrees or 180 degrees. So sine theta equals 0. Right. Remembering that our force is I, L, B sine of theta. And then I can also find the magnetic force on side B. Now again, I know that this magnetic force is equal to ILB sine theta. In this case, our sine theta term goes away because it's 90 degrees, and the sine of 90 degrees is 0. And I can also find the directions on these. Huh? Did I say 0? Yeah, I'm sorry. This is equal to 1, because as you said, sine of 90 is 1. All right. So I can find the direction of these forces on these loops. If I imagine here my current is up, my magnetic field is to the right, that means my force is into the page. So here on this side, I get a force that's into the page. What is the force that I feel on this side due to this wire? This is going to be out of the page. It's just going the opposite direction. So I have a force that's into the page and a force that's out of the page. So I have a force here that's into the page and a force here that's out of the page. So if I can imagine this loop, it's going to spin around when I run this current through this wire. I have one force going here, one force going here. And so this loop is going to spin like this. This side coming out, this side going in. All right. So on the left-hand side, out of the page, right-hand side, into the page. Alright, so now we, let's see, the forces on either side of the loop, F1 and F2, these are both equal in magnitude because I have the same current and I have the same magnetic field. I can calculate what the torque is on this coil of wire. What is this that we're talking about, by the way? This coil of wire with a current and magnetic field, what is that exactly?
It is a motor, right? So this is an electric motor, and this is the idea behind an electric motor. In fact, if you ever look inside those little electric motors, there's just a little coil of copper wire. They have a magnetic field inside of them. You run a current through them, and they spin around. I'm going to show you an animation of one. They're pretty cool how they work, but they're not real complicated. It's just a coil of copper wire. So we can calculate the torque. So if we want to know the torque output for one of these little electric motors, we can do that. It's pretty simple. Remember, my torque is equal to F times the length of the moment arm. I'm going to redraw that loop of wire over here. So here's my loop of wire. I have a force coming out of the page here and a force going into the page here. And remembering that this distance right here is A over 2. Because we said that side A was a distance A, a length A. So this torque then is just equal to our force times A over 2, but there are actually two forces that are equal in magnitude. All right. The magnitude of these forces are I times L times B times A over 2 plus I times L times B over A over 2. And these lengths L, that's this distance right here, this is L, this is equal to, with our loop, is equal to lowercase b. So I'm going to replace this with a lowercase b. If you want to leave it as an L, that's fine. But I'm going to replace it here with a lowercase b. Not the magnetic field, but the length of that wire. Now, the area of this loop is just A times B. Alright, it's a square. The area is A times B. And you notice here that I have this term A times B. So that's just our area. So this whole thing just simplifies very simply to just I times B times the area. So if I want to know the torque, and this actually holds for whether it's a square, a rectangle, or more commonly where it's a circular loop. You have a coil, a loop of wire, a circular loop. If you want to know the torque that's output by this little motor, it's going to be just the current times your magnetic field times your area. That's how you calculate the torque output of these motors. If you have more turns of wire, as usually the case, usually it's not just one turn of wire, but you have multiple turns, it just adds up. I mean, so our torque is just the number of turns in times the current times the magnetic field times the area. This is on your equation sheet. All right, let's try this question. Here I have a wire of negligible resistance. It spins into a rectangle, and a battery and resistor are connected. The right hand of the circuit extends into a magnetic field here. To test them, find the magnitude and direction of the net force on this circuit. Go ahead, I'll give you a couple minutes, head start. You want to find the magnitude of the force on this wire. So we have three little sections of wire here, 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 and here. All right, you want to think about the direction of the current. What is the direction of the current on this wire? I'll let you think about it. And then you want to calculate the magnitude of the current, the magnitude of the force on that current. Remember, F is equal to I L cross B. First thing you want to do is just find the current, and find the direction of the current, and then you want to do this cross product. Although, remember this is just I out inside theta, so it's pretty simple. What's the current now? 2 amps, right. On the law.
U equal IR, so I is V over R, 10 over 5. You might know the force? Okay, there are 3 sections of wire, but there's a force only on one section. Which section is that? The horizontal or vertical? Right, the vertical, right. These sections of wire are in the same direction as the magnetic field, so this is the only one that's going to be feeling a force. What is the direction of the current in this wire? It's down, right? Remember, current goes from high potential to low potential. Let me write that in there.
My current here is down. And my current is equal to V over R. That's 10 over 5. That's 2 amps. All right. And then that's basically done. What's my force? Know everything, right? Courtney, you were about to say it, weren't you? What's the force?
Oh, I didn't think that.
Oh, you haven't got it yet. Okay. You might have the force, Harley. I know my current is 2 amps. The length of the wire and the magnetic field is given us right here. Well, y'all know this. Huh? It's not 40. What were you saying?
I was saying the same thing.
No. Well, so I have 2 amps. Oh, I see what you're doing. Yeah. It's not 40 because it's 10 centimeters, which is 0.1 meters.
Oh.
Yeah, okay, yeah. So 2 amps, I understand. But I have 0.1 meters times 2 Tesla. So this is 0.4 newtons. And then let's see, is it in the K direction?
Well, it has to be either plus or minus K, right? Because my magnetic field is in the X direction, my current is in the Y direction. Yeah, it is plus K. That's plus K direction.
Alright, so it's 0.4 newtons in the K direction. Alrighty. Pretty straightforward kind of business. Yeah. Alright, we'll see some more. Let's try this quick test as well. This with your flickers. Oh, I don't think I've opened it yet. Hey, what did the how'd it go? What did the cross product say to the dot product? Come on, what did the cross product say to the dot product? Man, you've got no direction. Tell that to your calculus. That's gonna like it. I feel like it. Okay, so here I have a loop of wire and a magnetic field, and I just want to know in what direction does this loop turn, or actually what direction does it initially turn. We'll talk about that right now in just a second.
But what is the direction that it will turn? I have this loop of wire. This loop is coming out of the page. Looks like it's right here. It's going into the page here and out of the page, the current. What is the direction of the magnetic field going in this case? I have this permanent magnet north, south. What's the direction of it? To the left or right, the magnetic field? It's to the right. The magnetic field always goes from north to south pole. So my magnetic field is to the right. And I want to know what direction does this loop turn. Does it go clockwise, counterclockwise? Does not move at all? Or there's just not enough information? The axis here is this line.
Okay, looking pretty good. Most of you have the right answer. Alright, just a few more seconds. I'll stop at 110. 110. We have everybody but one, if I'm not mistaken. 3, 6, 9. There we go. Just skated in there, but who that was that clicked in? Who was it? Was it you? Yeah, you just skated in. Alright, so A is the right answer. That's very good. Clockwise, let me show you. So we just take each side separately. So here our magnetic field goes to the right. That's our B. I'm going to write this over here. So our magnetic field is here. Let's take this side right here. So our current is into the page, and then this will tell us the force on this section of wire. So current is into the page, magnetic field is in that direction, so my force is down. This is my force. So I have a force that's in this direction over here, and a force that's in this direction over here. So that means one side pulling down, one side pushing up, and it's going to rotate in a clockwise direction. All right, now what happens to this? It's kind of cool, actually. If you have a motor that's set up like this, I know that as it is here, that I'll have a force in this direction and a force in this direction. What happens to this loop when it flips over, when it turns from this direction all the way over to the other direction? Now look, what's going to happen is the side that's on the left will then be on the right. So where I had a current that was going into the page, now I'm going to have a current that's going in this direction, because this side will come over here, and this side will come over here. So now I'm going to have a current that's going in this direction. So if you notice here, I've switched the directions of the currents when it flipped over. So now my forces, I'll have one force going in this direction and another force going in this direction. So what's going to happen to this coil when it flips over? It's going to flip back over. That's not a very useful electric motor, right? If I have a coil of wire that flips over and then flips back over. So instead, this electric motor, the way it's built here, is just going to flip-flop. That's all it's going to do. It's just going to go back and forth. Right? And that's not very useful, because you can't translate that kind of motion to something that's really useful, right, to happen. You might be able to, but mostly you want an axis that is continually spinning. And then you'll, put that into a system of gears or whatever it is you want the axle to do. Okay, so this isn't very useful. So what you have to do is actually kind of clever. There are a couple ways you can get over this. So as the loop rotates, the force changes direction. When it's rotated 180 degrees, actually the force is opposite. In electric motors, you have to change the direction of the current. After each revolution, to keep this loop rotating in one direction. And we have two ways to do this. One, you can use a type of switch. Y'all use a switch in the lab to change the direction of current. What's that switch called? You remember? Right, the double throw switch, right? So that switch changes the direction of the current. That's that black switch. It has a couple different positions. Mostly, I think in lab y'all use it just as a simple switch, but you also in the magnetic field lab use it as a double throw. It actually changes the direction of the current. So use a type of switch like that changes the direction of the current. In motors, these are called brushes. You might have heard this term. I'm going to show you a little simulation. And they are used in DC motors. Let me show you this simulation. What these little brushes tell. Alright, let's look at a mass spectrometer. This is another application of this force on a moving particle. So we know that if I have a charge moving in a magnetic field, that the force is always perpendicular. And that type of force, the force that is always perpendicular to the velocity, is called what type of force? A centripetal force, right. So we talked about that last semester. Centripetal force is simply a force that's perpendicular to the velocity. And so a magnetic force, because of its nature, is a centripetal force. And so it's going to cause objects to move in a circular path. So let's say that I have this charge. It's a positive charge, and the direction of the force on this particle, if it's positive, is going to be up. So this particle will feel a force that's upward. If it's a negative particle, by the way, it's going to feel a charge, or a force rather, that's downward and will cause it to move in a circular path. Right? The force that it feels will depend upon the velocity. It'll also depend upon the charge and the magnetic field, right? F is equal to QB cross B. So we can find out a lot about that particle depending upon the path that it takes. So if theta is 90 degrees, as it is here, then our F is equal to QVB. And because it's a centripetal force, I can say that QVB is equal to mv squared over r. Remember where that v squared over r, that's our centripetal acceleration. And this relationship is what allows for a mass spectrometer, or a cyclotron. This is the cyclotron equation. This is on your equation sheet, but it's useful to know that this comes about from this expression, that it's just our magnetic force. It is a centripetal force. Right, so let's see, if I just solve this for r, I get rid of one of these v's, so r is mv over qb. So that's our cyclotron equation, and it just describes the radius of a path that a charged particle will take inside of a magnetic field. As I said, this is a mass spectrometer. You use this to identify the mass to charge ratio. So if you say you have an unknown particle and you want to know what that particle is, you can give it a certain velocity and run it through a magnetic field, and then you can determine what is its mass to charge ratio. This is how Agacho was obtained. Some famous scientists determined the mass to charge ratio of the electron, which was a pretty fundamental discovery at the time. The way he did it was to use this idea that if I put a charged particle through a magnetic field and measure its radius, then I can determine that mass to charge ratio. It's a pretty simple idea, but it's also very important just for sort of our understanding of atomic physics, or like understanding these particles. So let's see, I have this particle. Let's do a quick example. It has a velocity. I put it through a magnetic field, and then it has a radius when it goes through that magnetic field of about 16 centimeters, or 0.16 meters. And I want to know now what is the particle. So I have these known particles here, hydrogen, deuterium, tritium, and helium-3, and they all have known masses and charges. And so I can calculate what is their mass to charge ratio, and then compare it to my unknown particle. So I know that m over q is equal to rb over v. So let's see, r is 0.16 meters, b is 0.35 Tesla. That's a pretty big magnetic field, by the way. Usually your magnetic field would be a lot smaller than that, microtesla or whatever. And our velocity is 1.79 million meters per second, times 10 to the 6. And let's see, I get a mass to charge ratio of 3.13 times 10 to the 8th kilograms per coulomb. So which is it? Which particle is this in these list of known particles? It's going to be tritium, right? So since this matches up with this, then I know that my unknown particle here is a tritium particle. Nice way to determine unknown masses of unknown particles. And it's actually pretty simple to build one of these devices. So I know it sounds complicated, but it's not really. You use an electric field to accelerate them, right? And we know electric fields are going to give a very regular force to these charged particles, so we'll know its velocity. And then you can measure the radius pretty simply. All right, let's try this one on your own. Same process. Just calculate your mass to charge ratio. And here, I don't provide the mass to charge ratios, but you should be able to tell which particle it is once you get that mass to charge ratio. Notice they have all very different mass to charge ratios. well so far. About 15 or 20 more seconds. Stop at 205. That's going to be 205. A few more seconds. So let's say 205 or 210. I'll go to 210. Alright, A is right. So I find my mass to charge ratio, RB over V. And let's see, that is 0.052. Alright, so our particles, they went in a path that was about that big, a circular path about that big, about 5 centimeters across, or 10 centimeters across, rather. Our magnetic field is 0.4 Tesla, and then our velocity is 2 million meters per second. And that equals, it's like 1.0 something, right? What does it equal to? Times what? Times 10 to the negative 8. But you know, I can just look at these, since I know this ratio is a factor of 1, the only numbers up here that will give me a ratio that's anywhere close to a factor of 1 are those two numbers. But see, these two numbers, 3.35 and 1.6, that's more like a ratio of 2. This is more like a ratio of 3. And this is like a ratio of, I don't know, 1.5 or so. So you can go through and just determine this mass to charge ratio, 1.67 times 10 to the minus 27 over that charge is equal to this value. But you could also just look at the numbers. So A is the right answer. That's our hydrogen. All right. You want to see our pictures from yesterday? Okay. Got it pretty low on that. We went to the Global Wildlife Center. Have y'all ever been there? Mm-hmm. You've been, Harley? Have you been, Courtney, you've been there? Yeah, it was alright. It was kind of, I don't know. The animals are all very grabby. Like, they all wanted food. So, the kids really liked this. There was like a donkey or whatever out there. And this was just at the beginning. And there was an electric fence, too, that the kids all really liked. They're 4th graders, so there were about 12 4th grade boys all around the electric fence, touching it. It's like, ow, ow, ow. That's my son. Yeah, it's stupid, isn't it? Yeah, they put us all on these. That's my boy's friend, Ben. That's another friend of ours. But there were all sorts of these. These were like some sort of antelope. They would grab your cups and then run away with them and just eat the whole cup of food. Zebras, lots of zebras. You couldn't feed them by hand because they'd bite you. Oh yeah, see, there's one. The kids were throwing food into their mouths, like, and pouring it. They had a camel. It's kind of cool. They had giraffes, but they didn't come up. And then they had a bunch of longhorns as well. That was a longhorn. Oh, and then we went for ice cream afterwards. That's the end. That's it. Alright. Alright, let's look at the magnetic field of a long straight wire. We'll also look at the Biot-Savart law. A current in a wire creates a magnetic field that surrounds the wire. And to find the direction of this magnetic field, I'll show you how this comes about in this bit, but to find the direction, you use the right-hand rule. This is a little bit different application of the right-hand rule than we've seen before. You let your thumb of your right hand go in the direction of the current. All right, so far we have had two applications of the right-hand rule. The force on a charge and a magnetic field, and then the force on a current-carrying wire. And so this is our third application. If we let our thumb go in the direction of the current, then your fingers wrap around to give the direction of the magnetic field. Alright, so if I imagine this wire, there's a current flowing in this direction. I take my thumb and put it in the direction of that current, and then the magnetic field wraps around. So in this case, the magnetic field is going to go around like this. It's long been known that these wires have a magnetic field,
And people have well, Faraday was the first to map out these magnetic fields, Michael Faraday, and in the 1800s, and he found that this magnetic field surrounds our wire like this.
Right, and goes around. So we can use our right-hand rule to find the direction. So for example, what is the direction of the magnetic field produced by the current in this wire?
I have a current that's going up. What is the direction over here? Into the page. Thumb goes up like that, goes into the page. What about over here? Out of the page. What if I imagine a point out here to the right, and then a point behind the wire is going to be to the left? If I imagine this wire right here, my magnetic field goes around like that.
All right, so into the page on the right, out of the page on the left, and if I imagine points outside of the wire, they'll be going right or left if I'm in front of or behind the wire. All right, I can find the magnitude of this. I want to go through this quick derivation because it's kind of not useful so much. I doubt that you'll ever use it, but it's useful to sort of see how we think about these things. There is a law called the Biot-Savart law. It was determined experimentally. That means people just looked at these wires and they measured the magnetic fields, and they determined that the magnetic field is equal to mu naught I. Mu naught is the permeability of free space. ds sine theta divided by 4 pi r squared. I want to do the derivation. I'm not going to ask you to do the derivation, all right, but I want you to see it because it's just sort of useful. It's a nice way to think about how we calculate things like this. All right, so this is the magnetic field due to a small length of wire with a certain current through it at a distance. This is the distance from the wire, and this is our angle theta. Let me draw you a figure. So say I have a wire like this. I have a current that's coming up like this, and I want to know what is the magnetic field at this point. Now I know that the magnetic field, just due to my right-hand rule, looks like that. It's into the page. And this has been measured, and actually we can express the Biot-Savart law in terms of our cross product. All right, so it'll show us the direction of that vector. And then let's imagine that I have a small element of wire up here. I'm going to call it ds. There is a distance here and here. I'm going to call this big R. This doesn't change. Little r, this will change as I integrate over ds. All right, so I'm going to have a magnetic field that's into the page at this point that's due to this vector, this little element of wire, this differential element ds, is going to be into the page. Now I can integrate from here all the way to infinity. This is an infinitely long wire, and I'm going to get a magnetic field at this point. How will that magnetic field differ integrating from this point down? Or will it differ? Will it be the same, or will it be different direction? Will it be zero? What will it be? No, it's not. Will it be the same? It shall. Yes, it shall be the same. So if I integrate from here all the way to infinity, and here all the way to infinity, I'm going to get the same magnetic field for both sections of those wires. So I can say then that the magnetic field is equal to twice the magnetic field if I integrate from 0 to infinity. So this is our 0 point right here of dB. All right, putting in our Biot-Savart law for our magnetic field, this is going to be mu naught I over 2 pi times the integral of 0 to infinity of that sine theta ds over r squared. That's just sort of putting in this for dB, and then I cancel out this 4 and just get a 2 right here. I can do this integral. It's not a difficult integral. If I make some substitutions, I know that r is equal to the square root of s squared plus r squared. Excuse me, big R squared. Here, s is this distance on the triangle. And then I also know that sine of theta is equal to sine of 90 minus theta. That's a trig identity. You might see it as sine of pi minus theta. Notice my angle theta, by the way, is this angle. So these two are equal, and then that's equal to the square root of s squared over square root of r over square root of s squared plus r squared. Don't worry too much about that trig identity. You've probably seen trig identities like this before, right? Y'all use them in calculus? Yes? Okay. So if I substitute these in, I get this term. I get that b is equal to mu naught I over 2 pi integral from 0 to infinity of r ds, over s squared plus r squared to the 3/2. This is a common integral. You can find it in your, your integration tables, but y'all aren't allowed to use, are you, in calculus? Integration tables in calculus? But you know they exist, right? Yeah, so integration tables are really nice. They have all these common integrals, and this one is a common integral. You can find it in your integration tables. And it turns out that this all simplifies to this expression for the magnetic field of mu naught I over 2 pi r. All right, so that's how we find the magnitude of that magnetic field. And again, just I want you to sort of be exposed to this, where I integrate from here to infinity, recognizing that the magnetic field on both sides are the same, and then I can go through and make these substitutions based on trigonometry, integrate over that whole region. All right, so our magnetic field is given by that law, the mu naught I over 2 pi r. That's on your equation sheet. Though be careful, make sure that you're familiar with that equation sheet, because this equation is very similar to the magnetic field due to a coil of wire, which we're going to see next time. Here mu naught is the permeability of free space. Let's try this quick test question. Yeah, the I's are equal here, yeah. So I have a point A that's equidistant between two wires, and I have currents traveling in those wires that are equivalent currents, equal currents, one up, one down. What is our magnetic field? Each wire will generate a magnetic field at that point A. You want to ask yourself, what is the direction of that wire? Or what is the direction and what is the magnitude of those two magnetic fields due to those two wires? And then what happens to them? Alright, just a few more seconds. I'm going to stop at 120. 120. I'm doing pretty well. Okay, good. B is the right answer. Here, due to this wire, I get a magnetic field that's into the page over here and out of the page over here. And due to this wire, I imagine I get a magnetic field that's into the page over here and out of the page over here. So both of these magnetic fields will add up in order to give me a magnetic field that's out of the page. Now, if, for example, this current instead was going up, what would be the magnetic field? It would be 0, because I'd have one that was into the page and another that was out of the page. They'd be equal in magnitude, and because magnetic fields are vector quantities, those two vectors are going to add up to give us no magnetic field at all in the center. All right. I'm going to skip this one. I want to show you the idea of this. We'll see this again on the concept test, but it's kind of tedious. But here, if I have a point P right here and I want to know the magnetic field, I just take each point. So for example, this wire, which is out of the page, will cause a magnetic field that goes counterclockwise. So at this point, it's going to cause a magnetic field in that direction. This wire will cause a magnetic field like this, so it's going to cause a magnetic field like that. This wire like that, and this wire, is that right? Yeah, like that. Actually, it goes around like that. And you can go and add up all the vectors for those magnetic fields and figure out what is the direction of the magnetic field total. In this case, the magnetic field is going to be down. Right. You're not going to have one like this. This is kind of tedious because you have to go through 12 different wires and figure out the direction of the magnetic field. But you do need to know, be able to figure out what is the direction, what is the magnitude of the wire with a current traveling through it. You can do that, right? Listen, we're not having class on Friday, but let's see how much we have left here. No, we'll be okay. Let me do a couple more things. I have a few more minutes. Yeah, on Monday, we'll spend most of the class time, reviewing for the test, but we're going to have a couple more small things here. Let me just sort of give you what you need to know here in case you want to start doing the homework. Current carrying wire creates a magnetic field surrounding the wire. When another wire is in the field, it experiences a force due to this magnetic field. And so both of these wires are going to feel a force. We'll revisit this, okay? I know this is kind of fast. I just want to get this information out to you. I'm going to have a magnetic field due to this wire. I'll have a magnetic field up here that's in that direction. Due to this wire, I'm going to have a magnetic field down here in that direction. Two separate wires, two separate magnetic fields. As a result of this wire and this magnetic field, I'm going to have a force. And as a result of this wire and this magnetic field, I'm going to have a force. So these two wires that have currents in the same direction are going to suck together because the currents in each wire are going to interact with the magnetic field due to the other wire. I can figure out what these are. This is going to be I1L B2, the current in the first wire, times the magnetic field due to the second wire, which is I1L mu naught I2 over 2 pi r. I know this is fast. We can come back to this. And then F12 is negative of F21. They have the same magnitude. This is how we define the ampere. Guys, we'll come back to this. Let me go ahead and give you the next thing. Is the current loop B is equal to mu naught I over 2R. And if I have multiple turns of wire, this is for a loop of wire like this. If I have multiple turns of wire, it's just N mu naught I over 2R. And we'll talk about solenoids and how they work next time. We'll revisit these, okay, but in case you want to start working on this homework over the weekend, this is sort of the bare bones of what you need. All right, but on Monday, we'll sort of revisit these topics a little bit and do the rest of the quicker questions for this chapter. And then that'll be the exam. Multi-loop circuits, RC circuits, household circuits, and all of this business that we've been doing. All right, it's chapter 5. All right, guys, thank you. Y'all have a good day. Test next week, Wednesday. Opportunity to excel.